Hello viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about recovering the second stage. So let's dive deep into it. So what exactly is the problem? Because at this point in time, seeing a rocket first stage land is done. It's common. SpaceX is like, we got this. And every new company that is working on their new rockets, they're also like, it's sorted, it's done. It's one of those things that first one would be the most hardest one. It will take the most amount of time. Once it's done, everything else would be easily sorted. So we have reached that point. Like we got this. Like at this point in time, does humanity know how to make a rocket engine powerful enough, restartable enough, and reliable enough where it can be used in first stage boosters that lands? We good. We got it. However, second stage is the problem. We have not even a clue at this point in time how to handle second stage re-entry. And why is that? Well, problem is the booster. Booster puts a lot of energy in the second stage. To give you a context, like actual context of it, if you take Falcon 9 and you see wait for MECO, main engine cutoff, you will find that that puppy happens at 7,900 kilometer per hour, almost 8,000. Like sometimes it actually touches that kind of speed. So that's when they do main engine cutoff. So that amount of energy is the starting energy for velocity, so to say, is the starting velocity of second stage. Second stage starts at that. And second, give you weight constraint on this. Second stage is around 4 tons dry, and it goes up to like 92 tons when fully fueled. So heavy puppies, not very lightweight. And here's the most difficult part of it. The payload deployments happen on the second stage. So fundamentally, second stage is the one that is actually doing the home delivery. It's like doing the orbital delivery. That fundamentally means it's also traveling at orbital velocity, meaning if nothing is done to it, it will get stuck in orbit fundamentally. So that's a very serious problem. And second engine cutoff happens at orbital speed. Obviously, it has to be there. Now, and be mindful, this is just talking low Earth orbit. What if you have to do injection burn or much higher orbit? Your speed can go even higher. For example, in this mission, they are touching 35,000 kilometer per hour, second stage. And so whenever the engine cutoff will happen, it will be the payload velocity requirement. So fundamentally, you're talking about something that is in orbit. So that's a very complex problem to solve, because if you directly try to go bam with the atmosphere exactly like how first stage boosters do, this will happen to you. First stage booster is the easy, man. That barely goes to 8,000 kmph. That's like, bro, jump change. That's like hypersonic hulululu. Like even the Maverick plane supposed to go faster than that. So that's not that bad. The moment you go orbital velocity, this happens. It's like gone. Your stuff gone. Dust. This happens. So fundamentally speaking, it's ludicrously complex because of the velocities, speed required. Like the speed is bonkers. So the first solution is aerobraking. Now aerobraking is basically you dump the energy. Now thankfully Earth has an atmosphere and you can dump energy into it. It can actually eat up a lot of energy. So all the energy that your rocket put into the stuff, you dump into the atmosphere. Thankfully for rockets, there are some things that are making it easier. For example, it has deployed the payload. So payload mass gone. Fuel, majority of the fuel would have been burned. Fuel mass gone. Payload fairing, most designs generally would have discarded it. So that also gone. So your mass is much less. So the amount of energy you need to dump into the atmosphere, it's not that high. Like space shuttle was really bad design. So space shuttle really needed to dump a lot, like a lot, idiotically lot. So you have to dump all that energy into the stream. Basically, you are firing a rocket in reverse. Thankfully, Earth's gravitational well is also very deep. So you need a very small D cell to get captured by basically or from orbit to low Earth orbit, basically to falling orbit is super easy on Earth. You only need minor D cell. For example, space shuttle, when they had the 3 giant engines, there were 2 tiny engines on top. Those were orbit maneuvering engines. Those puppies were responsible for decelling it. Basically, you just detach from ISS and then you look back and then you fall. So it can be done without consuming too much fuel. So if you need fuel for that stage, it's not that brutal. It can be done. But you do need heat shield, otherwise you will melt. So flat out heat shield equals not melting. Without heat shield, you melt. This is critical. There is no option here. This is from Gemini. They had some film camera there to test that puppy out. And second stage has to be designed for it. For example, you may think, hey, what if I have a pointy structure going at orbital velocity? Well, this is the issue. If you have a pointy structure, the plasma line, basically the line where you have maximum heating, touches your structure. So that structure erodes. It's no go. So we learned through trial and error and studying meteoroids that we need blunt body. If you have blunt body, it's basically like a Jedi there. So Jedi goes, stop. So you create a plasma wall. Now benefit, this plasma wall is the hottest part. That's good. It's away from you. That's good. Problem, you still have heating. It's almost like how you have in Saturn V F1 engines. The engine bells were like huge. They needed cooling. So how the heck you cool engines? They flow cold gas through it. Now here's the real. How the heck you get cold gas? Well, cold is a relative term. The core gas was hot to like let's say 1000 degree to 1200 degrees Celsius. The outer gas, it was basically pre-burnt exhaust from the pre-burner. Pre-burner was like only 700 degrees Celsius. So 700 degrees Celsius was the cooling gas. So same thing happens here. Yes, your main heating area is away from you. That's good, awesome. But this area is not cold. You still need heat shield here. Now, only benefit is that the mean frictional, like absolute heating is here, and you are getting more photon-based heating. Now, why the heck photon is there? Well, this is making a plasma. Plasma radiate a lot of its energy using photons, generally infrared photons, and everything, it glows, like it literally glows. So it's dumping photon energy of every spectrum. So you need heat shield that can actually absorb that. Otherwise, you will be like slow cooked. So you do need that. And this is an example of fairings. Now, here's the deal. How the heck fairings are successfully able to re-entry without being a heat shield? There are few things working in their favor. First thing, they are huge in terms of surface area to kilogram. Basically, how much square meter is there per kilogram? These puppies are feather. They are like huge, lightweight, and you can even see them flexing. They're very lightweight structure, like very light. They're designed to be lightweight. So that helps them immensely. Meaning if atmosphere is like, you should slow down, they're like, okay, bro, okay, we good, we'll slow down. Second, they generally do not go at orbital velocities. Like, what? Well, here's the deal. If you watch any of the stream, you will see the moment a rocket clears the atmosphere, the moment they know for a fact that now atmosphere shielding is no longer required, payload fairings is yeet out of there. And you can see that payload fairings are yeeted and rocket still keeps going for quite further while. So these things never touch full orbital velocity. So these two things helps them. Like first, it never goes true orbital velocity. Second, it's a very large surface area and it's so lightweight that, and when atmosphere is like, you should slow down, they're like, okay, bro, okay, we're good. So that's how you do. But you can still see, like, it's not a chump change. Like, it's still a brutal heating it has to go through, but not as brutal as like full orbital velocity or 35,000 km per hour. The most brutal heat shield humanity ever built is in Apollo mission. That puppy just bammed into the Earth's atmosphere. I'm like, damn. So that's the aerobraking part of it. So how the heck Starship is supposed to be doing that? Well, some things are helping Starship. For example, mathematics, which is small rockets do not have a good scope where they can actually do second stage recovery. Can they try it? Absolutely, you can try it. But the viability from an economics point of view, from an engineering point of view, is like, why? Like, it's very brutal. The moment you make it big, the mass margins you have, basically how much mass you can go in one way or the another way, becomes exponential. Meaning if you have a rocket that's like, bro, I am 150 tons capable, and your payload is, let's say, only 100 ton, which, be mindful, it would be really big ass payload to be 100 ton. You'll be like, rocket is like, bro, I have 50 tons of headroom left. Like, I can carry that much extra fuel just so I can land safely, or do decel to slow myself down to such a low speed where the heating load is very minimal. So mass margin is the most critical aspect here. It has scope. If the larger the rocket, the more scope you get. And Starship from day one was designed to dump majority of its energy orbital velocity in using heat. Basically heat shields. Heat shields gonna dump all that energy into the atmosphere. And because it's a blunt body by design, it's gonna dissipate a lot of energy. So it needs heat shield, it got heat shield. And then we come to another aspect of engines. Now you can see there are 9 engines. 6 engines are vacuum optimized and 3 engines in the core that are sea level optimized. Now, like, do you really need that? Well, sea level ones, they need it because they need deep throttle capability. If they do deep throttle on vacuum optimized engines, yeah, no. And be mindful, there is a way to make a nozzle that is stable enough at sea level and efficient enough in vacuum level. That's exactly how space shuttle nozzles were designed. They had like a curve and then they curved inwards a little bit to make sure the flow separation does not happen. However, that fundamentally limits the throttle input, meaning how much throttle you can do in or out. Yeah, that's limited. If you do too much, boom happens. So for that reason, they're like, and be mindful, it's a compromise solution. Basically, for space shuttle, awesome. For this sort of design, not really that good, because it will not give them the maximum needed efficiency for vacuum. It will not give them maximum reliability needed for sea level. So it's like, it's neither here nor there. So for that reason, they're like, okay, we have 6 daddy engines that's going to take care of the space part of it. Once we have to do re-landing, like actually have to land, let's say they do minor desal burn, which I'm pretty sure they may not even need. Thrusters may be good enough to just slow them down enough where they can actually be captured by Earth. And then 3 core engines they will fire for landing burn, and in that time they need a deep throttle capability, and it will be like, I got this. So, and they need control surface because it's a big body. Again, control surface has become much more easier. So big bodies, basically those are small plane size surface area. So larger actually makes you far more effective in terms of designing a system that is reusable. Like if you try to do this sort of structure in, let's say, Electron rocket, yeah, the payload to the orbit would be like 2 kilogram. So this is the Starship. How the heck they are solving it? They have a heat shield to dump majority of the energy. They have control surfaces so they can actually manage the atmosphere effectively. They have 9 engines. Six of them are designed for vacuum operation, and 3 of them are like fine-tuned for robust operation at sea level. So this is how they are sorting it out. Then we come to the new entry right now, that is Stoke Space. Now Stoke Space, they are a new player. I have already covered them in a video, and they have some new ideas. So the idea is that they're going to use metal heat shield. Now the first red alert in your brain should be like, isn't metal melts before ceramic heat shield? Yes, they do. However, metal is a good conductor, meaning if you have a coolant flowing through them, you got this. So do they have coolant? Yes, they are choosing liquid hydrogen. So world's best coolant. They got it. Coolant is there. Now what the heck are you gonna do after you have heated up liquid hydrogen from almost absolute zero to boiling hot? What the hell you gonna do with that high pressure gas? Well, you're gonna drive pumps using that. So this rocket engine that they are using has expander cycle, meaning they take hydrogen, they expand it using heat, and then it goes through a turbine and dumps that excess gas. Now, if this flame that you are seeing is from that excess hydrogen, because again, if this was burning properly with proper 1:1 ratio, you should not see it because that will be steam. That's exactly what you are seeing around it. Now you're like, wait a minute, can't we see steams? No. If you ever see like superheated, like it's invisible. That's how you know it's like properly saturated steam. If it's not, if you're seeing white things, yeah, not superheated. So you can even see that in Space Shuttle. When Space Shuttle main engine starts, before the solid booster ignites, it's completely clear. So why the heck you are seeing that's excess? That's the excess hydrogen. It's a hydrogen-rich cycle, and be mindful, expander cycle is literally running only on hydrogen gas. So it's just like hydrogen gas. So that's why you can see the flames here. So they are doing that for hydrogen. They are getting the power. Okay, everything is good. But here's the deal. How the heck they're going to do in vacuum? Well, this is their design. So they're going to have tiny nozzles around a heat shield. So heat shield will be here, and they have tiny nozzles. Their mathematical calculation is for 30. This one was tested, if I'm not mistaken, by 15. And of course, they will upgrade to 31. So the mathematics and geometry is that it's going to create a what we call virtual aerospike. So if you fire any thruster in a pure vacuum, it creates a cone, right? You have velocity of the exhaust velocity, and then it creates a cone. Okay, but what if you have a lot of cones in a cone itself? So that creates a scenario where half of all the cone thruster's energy goes into the center. What does center have? High pressure zone, because you created it. So it creates a virtual aerospike engine, meaning it's very efficient in sea level, very efficient in vacuum. So now, is it as efficient as basically a giant nozzle? We do not have enough test data to say. In principle, it should be, but let's wait for actual testing data. But it should be more than good enough where it can actually work. Be mindful, this is not the only company that's trying this. Blue Origin also have some patents of something similar for their second stage recovery. Rather than recovering, basically, this gives them the advantage of like not needing heat shield too badly. Basically, here they are actually using heat shield for their advantage. They're like, hey, we have heat shield. What if we use it to, and again, if rocket engines are firing, it's creating the heat, hydrogen is boiling off, their turbines are getting pressure, so they do not even have to worry about it. So that's how they are doing that. So they're going to have 30 small units, 30 small those nozzles. Each of them has pental ejectors, and that's how they are doing the vectoring. That's how they're going to do thrust vectoring. So they should have very good fine-tuned control. They should be able to land. They should be able to withstand the re-entry without too much hassle, because again, they have hydrogen cooling the metal. So they're good. So this is the hope of Stoke Space. They have done already, this is the testing where just to figure out like, can they actually do throttle fast enough? Yes, they can. So that's a good test. Let's see for their system. And it would be interesting to see what actually happens when they launch this puppy in space. So what can we expect in the future? Well, here's the deal. Not everybody needs second stage reusable. For example, let's say you are rocket lab and you are working on electron rocket. Do you really need second stage reusability? Not really. So this is one of the things as specified. Like the larger the rocket you make, the more cost effective it becomes to reuse second stage. Same is not true for small rockets, medium rockets also. Big rockets benefits greatly, mathematically speaking, but small one, they may just end up with expensive R&D. And R&D cost is one of those things that you have to understand. It's brutal for the first company. For example, let's say SpaceX. If SpaceX did not have Elon Musk, as in like, and his persona that is collecting so much investor money, yeah, that SpaceX would have been poofed out of his, like, wait, don't they have a cheapest rocket? Not really. No, like, wait a minute. Is the rocket cheap? Absolutely. Are they recovering the rocket? Absolutely. But here's the, they did not just magically wake up one day and it's like, here's our reusable rocket. It took years of launching, years of like man hours that they spent on that puppy is exponential. They have to pay for that. So that becomes like billions of dollars spent. You are only seeing the rocket price. Oh, rocket is let's say $20 million and they are landing it. Let's say you spend 1 million just to refurbish it. You still have like $90 million savings. That's awesome. But yes, you may have spent like, billions of dollars in order to develop that technology. So expensive R&D is something that must be avoided if you are in a cost competitive environment. If you are not cost competing, like you can just charge whatever the heck you want to charge, go YOLO. But if you are in cost convert environment, this will lead to bankruptcy. Look into Virgin Orbit. Exact same thing. Like you can develop a technology. It's just like how much you spent to develop it. If you spent too much, now you have to charge too much from your customers, which customers will be like, bye, I'm going to someone cheaper. So this is the reason that not everybody is even thinking about second stage reusability. Booster gives you very quick return on your investment. So they're like, let's do this. And SpaceX have already done it. So it has, cat is out of the bag that it can be done. And the hassle, the first stage, again, like this is their second generation rocket that they are working on, neutron rocket. Every design principle of this is designed for to be very efficient. And you can see that in SpaceX also. They went from like block 1, block 2, block 3, and you can look into the Wikipedia and they can give you a change log, so to say, almost like a software, where it's like, oh, this was the issue, landing like so used to take too long, we had to literally unbolt it. Again, they learned it the hard way. That's why I said the expensive R&D part is hidden from us, but it's brutal for SpaceX. The accountant in SpaceX would be like, how much did we spend to figure out that we actually need to use this bolt rather than this bolt just so we can fold it up when we are bringing it inside? Yeah, money, lot of money. So small systems generally would benefit from a lower cost second stage. They will not benefit that much from, oh, we have second stage reusability. It's like, we may have spent too much just on that. So creating a Licofaco pen, basically we used to have a pen in childhood where you just write it and just eat it. Very cheap pen. So same thing with second stage of neutron rocket is designed that way. That is so cheap that it's just like you eat it and don't worry about it. And the fairings are basically locked into the chassis itself. So fairing literally lands on the ground. And again, they have learned from SpaceX mistakes. SpaceX tried to like catch the fairings and they're like, yeah, too expensive. Then they're like, hey, it can survive salty water for some time. It's like, okay, let's just land it and that's cheaper. But imagine what would be even cheaper if it comes back to you without touching water. It's like, so they're like, what if we bolt that puppy into the first stage? So this is the future side of things. Do not expect every upcoming startup to just like, we're going to reuse first stage and we're going to reuse second stage. It's like, do you really need to? Like Blue Origin is working on second stage recovery. But again, A, they are very secretive. B, they are working on big rockets. So they do have enough mass margin where they could be like justifiable. Can a small company do it? Let's just see. It can be done. Let that be very clear. This money part is the most expensive part, not the rocket itself, the R&D that you spent in order to get it. So this was my presentation on second stage recovery. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.